Gravitational waves, first predicted by Albert Einstein in 1915 through his theory of general relativity, have remained one of the most profound and elusive phenomena in modern physics. The concept of space-time fabric-like and capable of bending under the influence of mass and energy was groundbreaking. However, the prediction that massive, accelerating bodies could produce ripples in space-time seemed almost impossible to verify with the technology available at the time. The scientific community's interest in gravitational waves grew gradually over the 20th century. Initial skepticism stemmed from the absence of experimental evidence and the seemingly insurmountable technical challenges of detection. Unlike electromagnetic waves, gravitational waves interact weakly with matter, making them incredibly difficult to observe. The quest to detect these waves would span decades, requiring technological advancements that were not yet imaginable during Einstein's lifetime. In the early days of this pursuit, global circumstances added complexity to the task. The mid-20th century was marked by the Cold War, a period of intense geopolitical rivalry between the United States and the Soviet Union. While this era was dominated by fear of nuclear conflict, it was also an age of rapid scientific and technological progress. Space exploration became a powerful symbol of national pride and technological prowess. The space race drove investments in areas like rocketry, communication, and advanced research, indirectly contributing to the tools needed to pursue gravitational wave detection. During this time, scientists and engineers began developing increasingly sensitive instruments to detect cosmic phenomena. Key figures such as Joseph Weber, an American physicist, pioneered early efforts in gravitational wave detection. In the 1960s, Weber constructed large aluminum cylinders, hoping to observe vibrations caused by passing gravitational waves. His work inspired both hope and controversy. While Weber's initial claims of detection could not be replicated, his efforts laid the foundation for future research. The scientific community recognized the enormity of the challenge and the importance of collaboration. Various institutions around the world began to conceptualize more advanced detection methods. The idea of using laser interferometry, a method that could measure incredibly small changes in distance caused by gravitational waves, gained traction. This concept would eventually lead to the construction of large-scale projects like the Laser Interferometer Gravitational Wave Observatory, LIGO. The importance of these efforts cannot be overstated. Gravitational waves offer a new way of observing the universe, revealing events that are invisible to traditional telescopes. For example, phenomena like the collision of black holes or the merging of neutron stars generate gravitational waves that carry information about the extreme conditions of their origins. Detecting these waves would not only confirm a key prediction of general relativity, but also open a new frontier in astrophysics. The stakes were high. Success in this mission promised to revolutionize our understanding of the cosmos, but the risks of failure were equally significant. Critics questioned whether the technology needed to detect gravitational waves could ever achieve the necessary precision. Funding was another challenge, as governments often prioritized more immediate technological or military goals over abstract scientific research. Despite these hurdles, visionary leaders within the scientific community remained committed to the mission. They understood that the potential rewards, unlocking the secrets of the universe, were worth the long and uncertain journey. Collaborations between institutions, the establishment of global scientific networks, and the relentless drive of researchers gradually propelled the field forward. By the late 20th century, theoretical advancements and technological progress converged to create a renewed sense of optimism. Plans for large-scale interferometers, capable of detecting minuscule distortions in space-time, began to take shape. These ambitious projects symbolized the culmination of decades of effort, embodying the dreams of generations of scientists who had dared to imagine that humanity could one day listen to the universe through the medium of gravitational waves. As the 21st century dawned, the world stood on the brink of a scientific breakthrough that would forever change our perception of reality. Gravitational waves were no longer a distant theoretical concept. They were within reach. The race to detect them intensified, fueled by a global community united by a shared vision of discovery and exploration. This chapter in the history of science was just beginning, with the promise of unparalleled revelations waiting on the horizon. The journey to detect gravitational waves was fraught with early challenges. When Einstein first formulated the theory of general relativity, even he expressed doubts about whether gravitational waves could ever be observed. The ripples in spacetime predicted by his equations were expected to be extraordinarily small, on the scale of a fraction of an atom. Detecting such minute distortions seemed almost impossible with the technology available at the time. The early 20th century lacked both the conceptual tools and experimental infrastructure to seriously pursue this scientific goal. Despite these technological limitations, a few visionary scientists dared to explore the possibilities. One of the first pioneers, Joseph Weber, faced overwhelming skepticism from his peers when he proposed that gravitational waves might be detected through mechanical resonators. In the 1960s, Weber designed massive cylindrical aluminum bars, theorizing that gravitational waves would cause them to resonate slightly upon passing. He claimed to have detected signals, but his findings were not reproducible by others. The scientific community remained unconvinced, and Weber's credibility suffered. However, his work planted the seeds for a new generation of researchers who would build on his foundational ideas. Early research efforts were also hindered by a lack of adequate funding and resources. In a time dominated by the Cold War, governments focused heavily on defense and space exploration, with limited support for abstract scientific pursuits like gravitational wave detection. Research priorities leaned toward technologies with immediate strategic value, such as satellites, rockets, and nuclear advancements. This created a significant obstacle for scientists seeking funding for long-term, high-risk projects. Nonetheless, visionary leadership played a critical role in sustaining momentum. In the United States, the post-Sputnik era had sparked a renewed emphasis on science and technology. Figures like President John F. Kennedy had inspired a generation with their ambitious visions of space exploration and scientific achievement. Kennedy's famous 1962 speech at Rice University, where he declared that the United States would go to the moon within the decade, demonstrated the power of vision-driven leadership to mobilize resources and inspire innovation. While gravitational waves were not a central focus of national policy, the broader push for scientific advancement indirectly supported efforts to develop cutting-edge research infrastructure. International collaboration also became increasingly important. Scientists from different countries recognized the scale of the challenge and the need for shared expertise and resources. In Europe, for example, efforts to build gravitational wave detectors gained traction, culminating in the formation of projects like the Virgo interferometer in Italy. These collaborations demonstrated the value of pooling global talent and funding to tackle complex scientific questions. Theoretical challenges added another layer of difficulty from to new. Researchers needed to refine their understanding of gravitational waves and their sources. Einstein's equations were notoriously complex, and predicting the exact behavior of waves under various astrophysical scenarios required extensive mathematical modeling. Scientists had to account for factors like noise interference, cosmic background signals, and the behavior of extreme objects such as black holes and neutron stars. Each theoretical advance brought researchers closer to identifying potential methods of detection, but also revealed new complexities that demanded further study. Social skepticism compounded these obstacles. Many saw gravitational waves as an esoteric concept with no practical value. Critics questioned why governments and institutions should invest in such a speculative endeavor. Public understanding of theoretical physics was limited, and the concept of space-time itself was difficult to grasp. Scientists had to find ways to communicate the significance of their work to policymakers, the media, and the general public. Over time, they framed gravitational wave detection as part of a larger narrative about humanity's quest to understand the universe, drawing parallels to other groundbreaking discoveries in astronomy and physics. Despite the myriad challenges, optimism began to grow as technological advancements in other fields opened new possibilities. The development of lasers, for example, provided a potential solution for measuring incredibly small distances. Laser interferometry, first proposed in the 1970s, emerged as a promising method for detecting gravitational waves. By splitting a laser beam and sending the two parts along perpendicular paths, scientists could measure any differences in the time it took for the beams to travel. If a gravitational wave passed through the detector, it would stretch and compress space-time along the paths of the beams, causing measurable shifts in the laser's interference pattern. However, early prototypes of interferometers faced significant limitations. Environmental noise, such as seismic vibrations, temperature fluctuations, and human activity, could easily disrupt the sensitive measurements. Researchers needed to design detectors capable of isolating gravitational wave signals from these sources of interference. Achieving this level of precision required both technological innovation and engineering ingenuity. Visionary leaders within the scientific community worked tirelessly to secure support for these efforts. Figures like Rainer Weiss, Kip Thorne, and Ronald Drever, co-founders of the LIGO project, dedicated decades of their careers to overcoming the technical and organizational challenges of building a large-scale gravitational wave detector. Their work demonstrated a blend of theoretical brilliance and practical problem-solving as they navigated funding hurdles, bureaucratic delays, and scientific skepticism to push their project forward. The path to realizing LIGO was emblematic of the broader struggle faced by the field. It took years of planning, experimentation, and refinement to secure the necessary resources and infrastructure. By the 1990s, LIGO had evolved from a theoretical proposal to a full-scale construction project, with two massive interferometer facilities built in Hanford, Washington, and Livingston, Louisiana. These facilities represented the culmination of decades of effort, but success was far from guaranteed. Early data from LIGO's initial runs produced no detectable gravitational waves, prompting further upgrades and refinements. The determination to press on despite setbacks became a defining characteristic of the gravitational wave research community. Scientists understood that progress would be incremental, driven by a series of small victories rather than a single breakthrough. They drew inspiration from other landmark achievements in science, such as the discovery of radio waves, X-rays, and the cosmic microwave background radiation. Each of these discoveries had faced similar skepticism and technical challenges, but ultimately transformed our understanding of the universe. The early visionaries who championed gravitational wave research were motivated by a profound sense of curiosity and wonder. They believed that the universe had secrets waiting to be uncovered, and that the pursuit of knowledge was a fundamental part of the human experience. Their resilience in the face of adversity laid the groundwork for the eventual success of projects like LIGO and Virgo, setting the stage for one of the most remarkable discoveries in the history of science. As the field entered the 21st century, scientists stood on the brink of a new era in astrophysics. The challenges of the past had shaped a generation of researchers who were prepared to tackle the final hurdles to detection. They knew that the stakes were high, but also understood the transformative potential of their work. The detection of gravitational waves would not only confirm Einstein's predictions, but also open a new window into the cosmos, allowing humanity to observe the most extreme and violent events in the universe for the first time. The detection of gravitational waves was not the result of a single mind or isolated effort. It was a collective triumph, driven by a diverse group of scientists, engineers, administrators, and visionaries who dedicated decades to solving some of the most challenging problems in physics. The work was a testament to the importance of teamwork and collaboration, as experts from around the globe contributed their unique skills and insights to bring this historic achievement to fruition. One of the pivotal figures in this effort was Rainer Weiss, a physicist at the Massachusetts Institute of Technology, MIT. In the early 1970s, Weiss proposed the use of laser interferometry to detect gravitational waves, recognizing that traditional methods such as Weber bars were insufficient for the task. Weiss's background in precision instrumentation and his meticulous approach to problem-solving were critical to the development of LIGO's core technology. He devised a detailed plan, known as the Weiss Report, which outlined the technical requirements for a laser interferometer capable of detecting space-time distortions on the scale of less than 1,000th of a proton's diameter. Around the same time, Kip Thorne, a theoretical physicist at the California Institute of Technology, Caltech, was deeply engaged in studying the astrophysical sources of gravitational waves. Thorne's expertise in general relativity and his ability to explain complex phenomena in clear, accessible terms made him a key advocate for the project. He worked tirelessly to promote the importance of gravitational wave research to the broader scientific community, emphasizing the potential discoveries that could be made by observing events such as black hole mergers and neutron-star collisions. Thorne's theoretical contributions also helped refine the models that would later be used to analyze the signals detected by LIGO. Another crucial figure was Ronald Drever, a Scottish experimental physicist who joined Caltech to help lead the design and construction of LIGO's interferometers. Drever was known for his hands-on approach to experimentation and his deep intuition for solving practical engineering problems. His innovations in interferometer design, including improvements in mirror suspension systems and laser stabilization, were instrumental in increasing the sensitivity of the detectors. Despite occasional conflicts in leadership style, the collaboration between Weiss, Thorne, and Drever proved essential to the success of LIGO. These three scientists, Weiss, Thorne, and Drever, became the core team behind LIGO's development. But they were far from alone. The project grew to include hundreds of researchers, engineers, and technicians, all working toward a common goal. Teams were formed to address specific challenges, such as isolating the detectors from environmental noise, developing advanced computational algorithms to analyze data, and maintaining the infrastructure of the large interferometer facilities. One notable group within the LIGO collaboration focused on seismic isolation. Since gravitational waves cause minuscule distortions in spacetime, even the slightest ground vibrations could overwhelm the signals that LIGO was designed to detect. Engineers developed a sophisticated system of seismic isolation platforms and suspension mechanisms to minimize this interference. These platforms used multiple layers of springs, pendulums, and active feedback controls to dampen vibrations, allowing the detectors to operate with unparalleled sensitivity. Another key area of innovation involved the development of high-power lasers and ultra-precise mirrors. The mirrors, each weighing about 40 kilograms, were coated with special materials to reduce light absorption and minimize thermal noise. They were suspended in vacuum chambers to prevent air molecules from affecting the laser beams. Maintaining the stability and alignment of these components required constant monitoring and fine-tuning, as even microscopic shifts could compromise the experiment. The data analysis teams played an equally critical role. Detecting gravitational waves required processing vast amounts of data in real time, filtering out noise from natural and human-made sources. Scientists developed sophisticated algorithms based on matched filtering, a technique that compared incoming signals to a library of theoretical waveforms generated by simulations of astrophysical events. These algorithms enabled researchers to identify potential gravitational wave signals buried within the noise, reducing the likelihood of false detections. The LIGO Scientific Collaboration, LSC, eventually grew to include researchers from institutions around the world. Scientists from Europe, Asia, Australia, and other regions joined forces to share expertise and resources. This global partnership fostered a spirit of cooperation that transcended national boundaries, with teams exchanging ideas, conducting joint experiments, and refining detection techniques. Meanwhile, parallel efforts were underway in Europe, where the Virgo interferometer project was being developed by a consortium of French and Italian scientists. Virgo's design was similar to LIGO's, but it featured longer arms and additional engineering enhancements. The collaboration between LIGO and Virgo would later prove vital, as having multiple detectors operating simultaneously allowed researchers to triangulate the source of gravitational waves and confirm detections with greater confidence. Throughout the journey, many individuals contributed behind the scenes, often without public recognition. Engineers who designed and maintained the vacuum systems, technicians who calibrated the instruments, and administrators who secured funding all played indispensable roles. Their work exemplified the idea that scientific discovery is a collective endeavor, built on the dedication and expertise of countless people working in concert. Anecdotes from the project reveal the human side of the mission. For example, team members often worked long hours, enduring setbacks and moments of doubt. In one instance, after months of unsuccessful attempts to reduce noise in the detectors, a breakthrough came when a researcher discovered that a seemingly minor piece of equipment, a loose cable connector, was causing interference. This moment of triumph underscored the painstaking attention to detail required for such a complex experiment. The pressure to succeed intensified as LIGO's construction neared completion in the early 2000s. The project had faced criticism from some quarters, with skeptics questioning whether gravitational waves could ever be detected. Funding agencies demanded results, and the scientific community watched closely to see if the decades-long effort would pay off. The LIGO team remained resolute, driven by the belief that they were on the verge of a historic breakthrough. The first operational runs of LIGO, known as initial LIGO, did not detect any gravitational waves, prompting further upgrades and improvements. These setbacks were disappointing but not unexpected, as the team knew that achieving the necessary sensitivity would require continued refinement. By the mid-2010s, the advanced LIGO detectors were operational, featuring significant enhancements in laser power, mirror stability, and noise reduction. The determination of the LIGO team culminated on September 14, 2015, when the detectors recorded a signal matching the predicted waveform of a binary black hole merger. The event, named GW150914, marked the first ever direct detection of gravitational waves. The discovery was announced to the world in February 2016, sparking widespread excitement and acclaim. Weiss, Thorne, and Drever were awarded the Nobel Prize in Physics in 2017, but they were quick to emphasize that the achievement belonged to the entire collaboration. The success of LIGO and Virgo has since opened new frontiers in astrophysics, allowing scientists to observe events such as neutron star collisions and study the properties of black holes in unprecedented detail. The story of gravitational wave detection is a testament to the power of human ingenuity, perseverance, and teamwork, qualities that will continue to drive scientific exploration in the years to come. The detection of gravitational waves required groundbreaking technological advancements, many of which were unprecedented in the history of science. The success of the Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo project was due to a series of critical innovations in engineering, materials, science, optics, computing, and noise isolation. These breakthroughs were essential for achieving the extraordinary level of sensitivity needed to measure space-time distortions caused by gravitational waves, distortions smaller than 1,000th of the width of a proton. At the core of gravitational wave detection is laser interferometry, a technique that measures tiny differences in the length of two perpendicular arms by using light. The fundamental idea involves splitting a laser beam in two, sending each beam down separate paths that form the arms of an interferometer. The beams reflect off highly polished mirrors at the ends of the arms and return to a central beam splitter, where they are recombined. If a gravitational wave passes through the detector, it stretches one arm while compressing the other, creating a phase difference in the light beams. This change in phase alters the interference pattern, which can then be measured to infer the properties of the wave. In theory, the concept of laser interferometry is straightforward, but its practical implementation was anything but simple. The first major challenge was achieving the required precision and stability. Even the smallest environmental factors, seismic vibrations, thermal fluctuations, and acoustic noise, could disrupt the measurements. Early interferometers struggled with noise that masked any potential gravitational wave signals, prompting researchers to develop advanced noise isolation technologies. One of the most significant breakthroughs was the creation of multi-stage seismic isolation systems. The detectors needed to be shielded from ground vibrations caused by earthquakes, traffic, and even local weather conditions. Engineers designed a series of pendulum suspensions and active damping systems to isolate the interferometers from these disturbances. Each mirror in LIGO and Virgo was suspended by multiple layers of wires and springs, allowing it to remain almost perfectly motionless despite external vibrations. Active control systems, equipped with sensors and feedback mechanisms, continuously adjusted the suspension to maintain stability. Another major technological hurdle was the development of high-power, ultra-stable lasers. The interferometers required an extremely coherent and powerful laser source to minimize noise from photon fluctuations. Early prototypes used lower-power lasers, but these proved inadequate for the sensitivity needed to detect gravitational waves. Researchers eventually developed a 200-watt infrared laser, with advanced stabilization systems to maintain a consistent beam shape and intensity. This laser was capable of sustaining high power without generating excessive thermal noise, a critical factor for achieving the necessary precision. The mirrors at the ends of the interferometer arms were also a marvel of engineering. Each mirror, known as a test mass, was made from ultra-pure fused silica and weighed approximately 40 kilograms. The surfaces of these mirrors were polished to atomic-level smoothness, with coatings designed to minimize light absorption and thermal distortion. Even microscopic imperfections in the mirror surfaces could introduce noise into the system. So extensive quality control measures were implemented to ensure the mirrors met the strictest specifications. Maintaining the stability of the laser beams over several kilometers presented another set of challenges. The interferometer arms were housed in vacuum chambers to eliminate air-induced noise. These vacuum systems, among the largest in the world, extended over 4 kilometers at each LIGO facility. The chambers maintained a pressure lower than that of outer space, preventing air molecules from interfering with the laser beams. Constructing and maintaining such large-scale vacuum infrastructure required significant engineering expertise and resources. In addition to these physical components, advances in computational technology were crucial to the success of gravitational wave detection. The raw data collected by LIGO and Virgo contained vast amounts of noise from various sources. To extract meaningful signals, scientists developed sophisticated data analysis algorithms based on techniques like matched filtering. This process involved comparing the observed data to a library of predicted waveforms generated through computer simulations of astrophysical events. If the data matched a waveform with high statistical confidence, it was flagged as a potential gravitational wave event. Creating these waveform libraries required extensive numerical relativity simulations. Astrophysicists modeled scenarios such as binary black hole mergers, neutron-star collisions, and supernova explosions, using Einstein's equations of general relativity. These simulations were computationally intensive, often requiring supercomputers to run for days or weeks. The results provided templates that helped researchers identify the unique fingerprints of different types of gravitational waves. The need for global collaboration also drove technological progress. LIGO and Virgo operated as part of an international network of detectors, including smaller facilities like GEO 600 in Germany and KAGRA in Japan. Coordinating these detectors allowed scientists to triangulate the location of gravitational wave sources, improving the accuracy of their observations. This collaboration required the development of real-time communication systems and standardized data formats, enabling teams across continents to share information and synchronize their experiments. One of the most remarkable technological breakthroughs occurred during the transition from initial LIGO to advanced LIGO. The original LIGO detectors, which operated from 2002 to 2010, did not detect any gravitational waves despite their sensitivity being orders of magnitude greater than previous instruments. This outcome was not unexpected, as the detectors were still limited by noise and other technical constraints. However, the lessons learned from initial LIGO informed a series of upgrades that dramatically improved the detector's performance. Advanced LIGO, which began operations in 2015, featured several key enhancements. The seismic isolation systems were upgraded to provide even greater stability, and the laser power was increased to improve sensitivity. New techniques for squeezing light, a quantum optics method that reduces uncertainty in one aspect of a light wave while increasing uncertainty in another, were implemented to further reduce noise. These improvements collectively increased LIGO's sensitivity by a factor of 10, enabling it to detect gravitational waves for the first time. On September 14, 2015, advanced LIGO recorded a signal that matched the predicted waveform of a binary black hole merger. The event, known as GW 150,914, marked a historic milestone in physics. The detected signal was so strong that it was clearly visible in the raw data, a rare occurrence in an experiment designed to measure incredibly faint phenomena. The waveform showed the final moments of two black holes spiraling toward each other and merging, releasing an amount of energy equivalent to 3 solar masses in the form of gravitational waves. The detection of GW 150,914 validated decades of technological innovation and theoretical work. It confirmed Einstein's prediction of gravitational waves, and provided direct evidence for the existence of binary black hole systems. The achievement demonstrated that humanity had developed the capability to observe the universe in a completely new way, through the vibrations of space-time itself. Since that first detection, LIGO and Virgo have observed numerous additional gravitational wave events, including the merger of neutron stars in 2017. This event, designated GW 170,817, was particularly significant because it was observed both through gravitational waves and electromagnetic radiation, light. The simultaneous observation of these signals, known as multi-messenger astronomy, opened new avenues for exploring the cosmos. Scientists were able to study the properties of neutron stars, the origin of heavy elements like gold and platinum, and the dynamics of high-energy astrophysical processes. The technological breakthroughs achieved by LIGO and Virgo continue to inspire further advancements. Efforts are underway to develop next-generation detectors, such as the Einstein Telescope in Europe and the Cosmic Explorer in the United States. These future observatories will be even more sensitive, capable of detecting gravitational waves from events at greater distances and lower frequencies. They promise to deepen our understanding of fundamental physics, including the nature of black holes, the expansion of the universe, and the behavior of matter under extreme conditions. In summary, the technological achievements behind gravitational wave detection represent one of the greatest triumphs of modern science. The combination of precision engineering, advanced optics, noise isolation, and computational analysis enabled humanity to unlock a new observational window on the universe. These breakthroughs have not only confirmed a century-old prediction, but have also ushered in a new era of discovery that will shape our understanding of the cosmos for generations to come. The detection of gravitational waves was the culmination of several critical missions and events spanning decades. This chapter in scientific history is filled with moments of suspense, triumph, failure, and discovery, each contributing to the realization of one of the most ambitious projects in modern physics. From early attempts to capture gravitational waves with primitive equipment, to the momentous detection of GW 150,914, each mission and experiment shaped the path toward success. The earliest serious attempts to detect gravitational waves were carried out by Joseph Weber in the 1960s. Weber constructed large aluminum cylinders known as Weber bars, which were designed to resonate when gravitational waves passed through them. Weber reported positive results in his initial experiments, claiming that the bars detected signals that matched his expectations. However, the broader scientific community was unable to replicate his findings. Over time, doubts about his methodology and results led to widespread skepticism. Despite the failure of the Weber bars, these experiments played a crucial role in raising awareness of gravitational wave research. They inspired other scientists to think creatively about alternative detection methods, ultimately leading to the exploration of laser interferometry. The concept of using laser interferometry for gravitational wave detection was proposed by Rainer Weiss in the early 1970s. Weiss recognized that detecting gravitational waves required a level of precision that no existing technology could achieve. He envisioned an interferometer with arms several kilometers long, capable of detecting distortions in spacetime as small as a fraction of a proton's width. Weiss's ideas attracted the attention of Kip Thorne and Ronald Drever, both of whom shared his passion for gravitational wave research. Together, they formed the core leadership of the LIGO project. However, the early years were marked by numerous challenges, including difficulties in securing funding and skepticism from other scientists. Many considered the project too risky, given the lack of direct evidence for gravitational waves and the immense technical hurdles involved. Allowing construction to begin. 2 large facilities were built, one in Hanford, Washington, and the other in Livingston, Louisiana. These sites were chosen to minimize environmental noise and maximize the sensitivity of the detectors. By the 1990s, LIGO had evolved from a theoretical proposal to a full-scale experimental project. The first iteration of LIGO, known as Initial LIGO, began operations in the early 2000s. The detectors were capable of unprecedented sensitivity, but they still fell short of the precision needed to detect gravitational waves. Scientists spent years conducting test runs, refining the instruments, and addressing sources of noise. These early operations were both frustrating and educational. Although no gravitational waves were detected, data collected during this period provided critical insights into how to improve the detectors. Engineers identified numerous technical issues, including seismic noise, thermal noise, and laser instability, which needed to be resolved before the project could succeed. In 2010, LIGO was temporarily shut down to undergo extensive upgrades. The next phase, known as Advanced LIGO, promised to increase the detector's sensitivity by a factor of 10. Advanced LIGO began its first observation run in September 2015. The upgraded detectors featured enhanced seismic isolation, more powerful lasers, and improved mirror suspension systems. The team was cautiously optimistic but understood that success was not guaranteed. On September 14, 2015, just days after the detectors were activated, LIGO recorded a signal that would change the course of scientific history. The event, later designated GW 150914, displayed a distinct waveform consistent with the merger of two black holes. The signal lasted only a fraction of a second but carried immense scientific significance. The waveform showed two black holes, each about 30 times the mass of the Sun, spiraling toward each other before merging. In the final moments of the merger, the black holes released an enormous amount of energy in the form of gravitational waves, equivalent to 3 solar masses. The signal matched theoretical predictions with remarkable precision, confirming both the existence of gravitational waves and the reality of binary black hole systems. The LIGO team spent months verifying the data before announcing the discovery to the world on February 11, 2016. The announcement generated global excitement, marking one of the most significant scientific breakthroughs of the 21st century. Following the success of GW 150914, LIGO continued to observe additional gravitational wave events. Each detection provided new insights into the behavior of black holes, neutron stars, and other astrophysical phenomena. In 2017, the Virgo detector in Italy became operational, joining LIGO in the hunt for gravitational waves. The inclusion of Virgo significantly enhanced the network's capabilities. By combining data from multiple detectors, scientists were able to pinpoint the locations of gravitational wave sources with greater accuracy. This collaboration was crucial for a major event that occurred later that year. On August 17, 2017, LIGO and Virgo detected a new type of gravitational wave signal. Unlike previous detections, which involved black hole mergers, this event, known as GW 170817, originated from the collision of two neutron stars. The signal lasted for over a minute and was accompanied by electromagnetic radiation, including gamma rays, visible light, and radio waves. This event marked the dawn of multi-messenger astronomy, a new era in which scientists could observe cosmic events through both gravitational waves and traditional electromagnetic signals. Telescopes around the world quickly focused on the source of the signal, located in a galaxy about 130 million light-years away. The data revealed details about the formation of heavy elements, the structure of neutron stars, and the dynamics of high-energy astrophysical phenomena, demonstrated the immense scientific potential of gravitational wave astronomy. It provided a wealth of information about the universe and underscored the importance of global collaboration between gravitational wave observatories and traditional telescopes. Not all missions were without setbacks. During LIGO's early years, technical failures and noise interference frequently jeopardized data collection. One notable crisis occurred when an unexplained noise source disrupted multiple observation runs. After extensive investigation, the team discovered that the noise was caused by a faulty vacuum seal in one of the detector arms. The incident highlighted the importance of meticulous maintenance and continuous monitoring of the instruments. These challenges served as valuable learning experiences, leading to further improvements in detector design and data analysis techniques. The resilience of the LIGO and Virgo teams became a defining feature of the project, as they repeatedly overcame obstacles to achieve their scientific goals. Since the first detection, LIGO and Virgo have observed dozens of gravitational wave events, each contributing to a growing catalog of cosmic phenomena. These discoveries have deepened our understanding of black holes, neutron stars, and the nature of space-time itself. They have also provided new tests of general relativity, confirming Einstein's predictions with unprecedented precision. The impact of gravitational wave astronomy extends beyond astrophysics. It has inspired advancements in quantum optics, precision engineering, and data science. The success of LIGO and Virgo has also demonstrated the power of long-term investment in fundamental research, paving the way for future projects like the Einstein Telescope and Cosmic Explorer. With new detectors on the horizon, the field of gravitational wave astronomy is poised for continued growth. Future observatories will be capable of detecting waves from a wider range of sources, including supermassive black holes and the early universe. These advancements promise to unlock new mysteries and further our understanding of the cosmos. The journey to detect gravitational waves has been one of the most remarkable achievements in scientific history. It stands as a testament to human curiosity, perseverance, and the relentless pursuit of knowledge, qualities that will continue to drive discovery for generations to come. The journey to detect gravitational waves was not without moments of crisis. Despite careful planning and engineering, the complexity of the instruments and the sensitivity required meant that small problems could rapidly escalate into significant setbacks. Over the course of several decades, LIGO and Virgo faced numerous technical, environmental, and administrative challenges. However, these moments of failure ultimately became opportunities for resilience, innovation, and collaboration, as the teams worked tirelessly to recover from adversity. One of the earliest and most persistent challenges faced by LIGO was the issue of environmental noise. Gravitational waves produce distortions in space-time that are incredibly faint. To detect them, the instruments needed to be sensitive enough to measure length changes smaller than a proton's diameter. However, this extreme sensitivity also meant that even the smallest environmental disturbances, such as seismic activity, human movement, or thermal expansion, could produce noise that overwhelmed any potential signals. During LIGO's early operational runs, noise contamination became a recurring crisis. For instance, ground vibrations caused by nearby trains and heavy trucks frequently introduced false signals into the data. Additionally, microseismic activity, often generated by ocean waves crashing on distant shores, created a constant low-frequency noise that interfered with the detectors. The team had anticipated these issues, but found that their existing noise isolation systems were insufficient. In response, engineers developed a more advanced seismic isolation system, incorporating multi-stage pendulum suspensions and active feedback controls. These improvements significantly reduced the impact of ground vibrations, allowing the detectors to achieve a new level of stability. However, each iteration of upgrades required time, funding, and extensive testing, delaying the project's progress. LIGO also faced several crises caused by technical malfunctions in research. One of the most significant incidents occurred during a test run when researchers noticed unexplained noise at a critical frequency. After weeks of investigation, the team discovered that a vacuum seal in one of the interferometer arms had failed, allowing air molecules to enter the chamber and interfere with the laser beams. Fixing the problem required temporarily shutting down operations and resealing the vacuum system, a time-consuming process that disrupted the experimental schedule. On another occasion, a faulty electrical component caused intermittent data corruption, leading to the loss of valuable observation time. The component was part of the system that monitored the alignment of the laser beams, and its malfunction created false alarms that appeared similar to gravitational wave signals. The team implemented new diagnostic protocols to detect and prevent similar issues in the future. These technical crises underscored the importance of redundancy and continuous monitoring. From that point forward, LIGO's engineers installed backup systems and enhanced the detector's ability to self-diagnose potential failures. This approach reduced downtime and improved the reliability of the experiment. In addition to technical crises, the LIGO project faced significant political and financial pressures. The early years of the project were marked by skepticism from funding agencies and the broader scientific community. Many questioned whether gravitational waves could ever be detected, given the scale of the technical challenges and the lack of prior evidence. Some policymakers viewed the project as an expensive gamble, with little immediate practical benefit. At several points, the project came close to losing funding. In one particularly tense period in the 1990s, the National Science Foundation, NSF, considered reducing LIGO's budget due to concerns about slow progress and escalating costs. The LIGO leadership had to make a strong case for the project's long-term scientific value, emphasizing its potential to revolutionize our understanding of the universe. Support from influential advocates, including Nobel laureates and prominent researchers, helped turn the tide. These supporters highlighted the importance of investing in fundamental research, drawing comparisons to other major scientific milestones, such as the discovery of the Higgs boson and the cosmic microwave background radiation. Their efforts ultimately secured continued funding, allowing LIGO to move forward with construction and upgrades. No large-scale project is immune to human error, and LIGO was no exception. Miscommunications and conflicting priorities occasionally led to delays and setbacks. For example, during a critical upgrade phase, a misunderstanding between teams working on different components of the interferometer resulted in a misalignment of one of the laser systems. Resolving the issue required reassembling part of the apparatus, costing valuable time and resources. The complexity of the project also posed organizational challenges. LIGO and Virgo were collaborative efforts involving hundreds of researchers from multiple institutions across different countries. Coordinating these efforts required clear communication, well-defined roles, and effective leadership. Over time, the project teams developed more robust management structures, including regular meetings, detailed documentation, and shared project timelines. One of the key lessons learned was the importance of fostering a culture of transparency and problem-solving. Team members were encouraged to report problems early and collaborate across disciplines to find solutions. This approach helped prevent small issues from escalating into major crises. When LIGO detected its first gravitational wave signal, GW150914, on September 14, 2015, the team knew they had made a historic discovery. However, they also understood that extraordinary claims required extraordinary evidence. The months that followed were filled with intense scrutiny and internal debate. Researchers conducted exhaustive checks to rule out alternative explanations, such as instrument malfunctions, noise contamination, and data processing errors. The crisis during this phase was not technical but psychological. The pressure to get the announcement right weighed heavily on the team. If the discovery were later discredited, it would not only damage the credibility of LIGO, but also set back the entire field of gravitational wave research. To ensure the integrity of their findings, the researchers enlisted external reviewers and performed multiple independent analyses. Ultimately, the team's meticulous approach paid off. When the discovery was announced in February 2016, the scientific community and the public responded with awe and admiration. The detection was confirmed by multiple lines of evidence, silencing the skeptics and solidifying LIGO's place in scientific history. The crises faced by LIGO and Virgo ultimately strengthened the projects by forcing the teams to innovate and adapt. Each setback prompted new research, technological improvements, and procedural changes that enhanced the detector's performance. For example, the development of quantum noise reduction techniques, such as squeezed light, was a direct response to challenges encountered during early observation runs. These techniques have since become standard in precision optics experiments. The experience also reinforced the importance of global collaboration. The partnership between LIGO, Virgo, and other observatories like KAGRA in Japan has enabled scientists to cross-verify their findings and improve the accuracy of gravitational wave detection. This international network continues to grow, with plans for next-generation detectors that will be even more resilient to noise and technical failures. The story of gravitational wave detection is a testament to the resilience of the scientific community. Despite facing numerous crises, the researchers involved in LIGO and Virgo never lost sight of their ultimate goal. They demonstrated that failure is not an endpoint but a stepping stone on the path to discovery. Today, the field of gravitational wave astronomy is thriving. Each new detection adds to our understanding of the cosmos, revealing phenomena that were once purely theoretical. The lessons learned from LIGO and Virgo will continue to guide future generations of scientists as they explore the frontiers of knowledge. The journey toward the detection of gravitational waves reached its dramatic climax with the successful observation of GW 150,914 on September 14, 2015. This moment marked the culmination of decades of research, technological innovation, and relentless determination. The goal that had once seemed unreachable was finally within grasp. The events leading up to and surrounding this detection were filled with anticipation, suspense, and ultimately, profound triumph. After years of upgrades and refinements, advanced LIGO was finally ready for its first observation run in 2015. The stakes were incredibly high. With sensitivity improved by a factor of 10 over the original LIGO detectors, expectations were cautiously optimistic. The team knew that if gravitational waves were detectable within the range of their instruments, they might observe a signal within the first few months of operation. However, the researchers were also prepared for the possibility that the run might not yield any detections. After all, gravitational wave events, particularly those from binary black hole mergers, were still thought to be rare occurrences. The data would have to be collected, analyzed, and scrutinized with extreme care to avoid false positives. In the weeks leading up to the start of the observation run, every component of the detectors was tested and calibrated. The vacuum systems, mirrors, lasers, and seismic isolation platforms underwent final adjustments to ensure maximum stability. Data analysis teams refined their algorithms to quickly filter out noise and identify candidate events. The atmosphere among the LIGO teams was a mixture of tension and excitement. Just days after the observation run began, on September 14, 2015, at 9:50 Coordinated Universal Time, a signal arrived at the detectors. The event was recorded almost simultaneously at both LIGO sites, Hanford and Livingston, allowing the team to immediately verify that the signal was not caused by local noise or interference. The waveform displayed the telltale characteristics of a gravitational wave, a rapid chirp pattern that matched the predicted signal from a binary black hole merger. The scientists quickly realized the potential significance of the signal. Early analysis suggested that the source involved two black holes, each roughly 30 times the mass of the Sun, spiraling inward and merging in a violent collision. The final merger had released an astonishing amount of energy, equivalent to the mass of 3 suns, in the form of gravitational waves. This energy had traveled across more than 1 billion light-years of space before reaching Earth. Despite the clarity of the signal, the team knew they had to proceed with caution. Gravitational wave detection had never been achieved before, and extraordinary claims required extraordinary evidence. Over the following weeks, researchers conducted extensive tests to rule out alternative explanations. They examined every aspect of the detectors, searching for possible sources of noise or instrumental error. The data analysis teams performed multiple independent checks to confirm the integrity of the signal. After months of analysis, the team concluded that the signal was indeed a genuine detection of gravitational waves. The event was designated GW 150,914, signifying the date of the detection. For the scientists involved, this moment was both exhilarating and surreal. The prediction made by Einstein a century earlier had finally been confirmed. Gravitational waves were no longer theoretical, they were a measurable reality. The news of the discovery was kept under strict confidentiality until the team could prepare a formal announcement. Internal meetings were filled with a sense of history in the making. Researchers reflected on the long road that had brought them to this point, from Joseph Weber's early experiments to the technological breakthroughs that had enabled LIGO's success. The gravity of the moment was not lost on anyone. On February 11, 2016, the LIGO Scientific Collaboration held a press conference to announce the discovery. The event was streamed live and covered by major news outlets around the world. Rainer Weiss, Kip Thorne, and other key figures in the project explained the significance of the detection, emphasizing the role of global collaboration and the decades of effort that had led to this moment. The announcement sparked a wave of excitement and fascination. Headlines proclaimed the beginning of a new era in astrophysics. Scientists, journalists, and members of the public alike marveled at the ability to listen to the universe through gravitational waves. For many, the detection was a reminder of the power of human ingenuity and the importance of investing in fundamental research. The discovery was celebrated as a landmark achievement, earning widespread acclaim and numerous awards. In 2017, Weiss, Thorne, and the late Ronald Drever were awarded the Nobel Prize in Physics for their contributions to gravitational wave detection. However, the recipients were quick to emphasize that the achievement belonged to the entire LIGO and Virgo collaborations, which included hundreds of scientists and engineers from around the world. The detection of GW 150,914 was a watershed moment in science, with profound implications for both physics and astronomy. For one, it confirmed a key prediction of general relativity, reinforcing the validity of Einstein's theory even under extreme conditions. The event also provided the first direct evidence for the existence of binary black hole systems, which had previously been hypothesized but never observed. In addition, the discovery opened a new window into the universe. Gravitational waves offer a unique way to study phenomena that are otherwise invisible to traditional telescopes. Unlike light, which can be absorbed or scattered by matter, gravitational waves travel through space-time largely unimpeded. This means they carry pristine information about their sources, allowing scientists to explore events that occur in regions of intense gravity, such as the cores of black holes and neutron stars. The detection also demonstrated the power of multi-detector networks. By having two detectors, one in Hanford and one in Livingston, LIGO was able to verify the signal with greater confidence and localize the source to a region of the sky. This capability would later be enhanced by the addition of the Virgo detector, enabling even more precise localization of future events. In the months and years following the detection of GW 150,914, LIGO and Virgo observed numerous additional gravitational wave events. Each new detection expanded the catalog of known cosmic phenomena, providing valuable data on the population of black holes and neutron stars in the universe. Notable events included GW 151,226, a second binary black hole merger detected in December 2015, with smaller black holes than those in GW 150914. GW 170,104, a merger observed in January 2017, further confirming the existence of binary black holes across a range of masses. GW 170,817, the first detection of a binary neutron star merger, accompanied by electromagnetic signals. This event marked the beginning of multi-messenger astronomy. These discoveries solidified gravitational wave astronomy as a vital and growing field of research. Scientists began using gravitational waves to test fundamental theories of gravity, explore the properties of dense matter, and study the formation of heavy elements. For the scientists who had dedicated their careers to the search for gravitational waves, the discovery of GW 150,914 was a deeply emotional experience. Many described it as a moment of vindication after years of hard work, doubt, and setbacks. Some reflected on the legacy of earlier pioneers, such as Joseph Weber, who had laid the groundwork for the field despite facing intense skepticism. The discovery also resonated with the public, inspiring awe and curiosity about the mysteries of the universe. It served as a reminder of the enduring human drive to explore and understand the cosmos, even in the face of seemingly insurmountable challenges. The success of LIGO and Virgo has had a lasting impact on science and technology. The techniques developed for gravitational wave detection have found applications in fields ranging from precision metrology to quantum optics. Moreover, the discovery has inspired a new generation of scientists to pursue careers in astrophysics and engineering. Looking to the future, plans are underway to build next-generation detectors, such as the Einstein Telescope and Cosmic Explorer. These observatories will be capable of detecting gravitational waves from even more distant and powerful sources, including supermassive black hole mergers and the early universe. The story of GW 150,914 and the broader quest to detect gravitational waves is a testament to the power of human collaboration, creativity, and perseverance. It stands as one of the greatest scientific achievements of the modern era, paving the way for new discoveries and a deeper understanding of the cosmos. The discovery of GW 150,914 and subsequent detections of gravitational waves have had a profound and lasting impact on both the scientific community and society at large. This chapter reflects on the immediate aftermath of the discovery, the long-term influence on various fields of research, and the broader legacy of gravitational wave detection. It also examines how the lives of the key figures and teams were changed by their historic achievement. When the discovery of GW 150,914 was announced on February 11, 2016, the global response was overwhelmingly positive. News of the detection spread rapidly, with headlines proclaiming the birth of a new era in astronomy. Media outlets, scientific journals, and educational institutions seized the opportunity to explain the significance of gravitational waves to a broad audience. Public interest surged, fueled by the sheer wonder of being able to listen to the universe through the vibrations of spacetime. The detection was particularly exciting because it represented a direct confirmation of Einstein's prediction, made over a century earlier. For many, the discovery served as a reminder of the enduring power of theoretical physics and the importance of long-term investment in fundamental science. Scientists and engineers who had worked on the project received widespread recognition, and the discovery was celebrated at universities, research institutions, and conferences around the world. In the months following the announcement, the LIGO and Virgo collaborations received numerous accolades for their achievement. The most prestigious of these was the 2017 Nobel Prize in Physics, awarded to Rainer Weiss, Kip Thorne, and Ronald Drever posthumously. The Nobel Committee praised the trio for their decisive contributions to the development of LIGO and the detection of gravitational waves. The award ceremony was a deeply emotional moment for the scientific community, for Weiss, Thorne, and other key figures expressed their gratitude to the hundreds of researchers and engineers who had contributed to the project. They emphasized that the discovery was a collective effort, made possible by decades of collaboration, persistence, and innovation. In addition to the Nobel Prize, the LIGO and Virgo collaborations received other major honors, including the Breakthrough Prize in Fundamental Physics and the Gruber Cosmology Prize. These awards brought further visibility to the field of gravitational wave astronomy and inspired young scientists to pursue careers in physics and engineering. The detection of GW 150,914 fundamentally changed the landscape of astrophysics. Gravitational wave astronomy quickly established itself as a vital new tool for exploring the universe, offering insights that were previously inaccessible through traditional electromagnetic observations. Some of the key scientific impacts include confirmation of general relativity. The observed waveform of GW 150,914 matched theoretical predictions derived from Einstein's equations with remarkable accuracy. This provided yet another confirmation of general relativity, even under the extreme conditions of a binary black hole merger. Discovery of binary black hole systems. Prior to GW 150,914, binary black holes were largely theoretical. The detection confirmed their existence and provided data on their masses, spin rates, and dynamics. Subsequent detections revealed that such systems are more common than previously thought. Multi-messenger astronomy. The detection of GW 170,817 in 2017, involving a binary neutron star merger, demonstrated the potential of combining gravitational wave observations with electromagnetic signals. This event provided critical information about the formation of heavy elements and the structure of neutron stars, opening a new era of multi-messenger astronomy. Expansion of cosmic observations. Gravitational waves offer a unique way to probe the universe, including regions that are otherwise obscured by dust and gas. Scientists have begun using gravitational wave data to study the evolution of galaxies, the behavior of compact objects, and the conditions present in the early universe. The technological innovations developed for gravitational wave detection have had a ripple effect across multiple fields. Some of the most significant advancements include precision optics and quantum technologies. The techniques used to stabilize high-power lasers and reduce quantum noise have influenced research in quantum optics and metrology. These technologies are now being applied to fields such as secure communication and advanced imaging. Seismic isolation systems. The sophisticated seismic isolation systems developed for LIGO have inspired new approaches to vibration control in other scientific instruments, including particle accelerators and space-based observatories. Data processing and machine learning. The algorithms used to analyze gravitational wave data have contributed to advancements in data science, particularly in the areas of signal processing and machine learning. These methods are being adapted for use in medical imaging, climate modeling, and other applications. The success of LIGO and Virgo demonstrated the power of international collaboration in tackling complex scientific challenges. Researchers from the United States, Europe, Japan, and other countries worked together to build and operate a network of gravitational wave detectors. This collaborative spirit has continued to grow, with plans underway for next-generation observatories like the Einstein Telescope and Cosmic Explorer. The gravitational wave community has also prioritized open science and data sharing. The LIGO and Virgo collaborations have made their data publicly available, allowing researchers worldwide to contribute to the analysis and interpretation of events. This openness has accelerated the pace of discovery and fostered new partnerships across disciplines. For the scientists, engineers, and students who worked on gravitational wave detection, the experience was often life-changing. Many described a profound sense of fulfillment and pride in being part of such a historic achievement. Some reflected on the personal sacrifices they had made, long hours, periods of uncertainty, and professional setbacks on the path to success. In interviews and memoirs, key figures like Rainer Weiss and Kip Thorne have spoken about the emotional highs and lows of the journey. Thorne, in particular, has emphasized the sense of wonder that drove him to pursue gravitational wave research, despite the initial skepticism surrounding the field. Weiss has often expressed his gratitude for the teamwork and mentorship that sustained the project through its most challenging moments. Younger researchers who joined the collaborations in the later stages of the project have described the experience as transformative for their careers. Many have gone on to take leadership roles in new gravitational wave observatories, ensuring that the legacy of discovery continues. The discovery of gravitational waves has had a profound impact beyond the scientific community. It has inspired curiosity and wonder about the universe, drawing attention to the importance of basic research in advancing human knowledge. Educational initiatives, documentaries, and popular science books have helped bring the story of gravitational wave detection to a global audience. The success of LIGO and Virgo has also served as a powerful example of what humanity can achieve through perseverance, collaboration, and a commitment to discovery. In a world often divided by political and social conflict, the achievement stands as a testament to the unifying power of science. Looking ahead, the future of gravitational wave astronomy, the legacy of GW 150,914, and the subsequent detections is still unfolding. Future observatories such as the Einstein Telescope in Europe and Cosmic Explorer in the United States are being designed to push the boundaries of gravitational wave detection even further. These next-generation detectors will be capable of observing events from much deeper in the universe and across a broader range of frequencies. Scientists are particularly excited about the potential to study supermassive black holes, primordial gravitational waves, and the early universe. These discoveries could provide insights into some of the most fundamental questions in physics, including the nature of dark matter, dark energy, and the origin of spacetime itself. In conclusion, the aftermath and legacy of gravitational wave detection are characterized by scientific breakthroughs, technological innovation, and a renewed sense of wonder about the universe. The discovery of GW 150,914 was not just an endpoint, but a beginning, a gateway to a new era of exploration and understanding. It stands as one of the most remarkable achievements in the history of science, inspiring generations to come. The discovery and detection of gravitational waves offer profound insights not only into the universe but also into the enduring themes of human endeavor. This chapter explores the broader themes and lessons from this achievement, including humanity's drive for discovery, the importance of perseverance in the face of adversity, the ethics of scientific exploration, and the role of collaboration in advancing knowledge. At the heart of the quest to detect gravitational waves is humanity's innate curiosity and desire to understand the cosmos. From ancient astronomers mapping the stars to modern physicists probing the fabric of spacetime, this drive for discovery has propelled countless scientific advances. The search for gravitational waves was motivated not by immediate practical applications, but by a deeper need to answer fundamental questions about the nature of reality. Einstein's prediction of gravitational waves in 1915 was revolutionary, challenging existing notions of space and time. For decades, scientists pursued the idea despite the lack of experimental evidence, driven by the belief that understanding the universe on a deeper level was worth the effort. This spirit of exploration is a defining characteristic of science, and one of the core reasons for humanity's progress in fields ranging from physics to medicine. The success of LIGO and Virgo illustrates that pursuing long-term, high-risk research can yield extraordinary rewards. The lessons learned from this endeavor reinforce the importance of investing in basic research, even when the outcomes are uncertain. History has shown that many groundbreaking discoveries, including gravitational waves, were initially dismissed as impractical or impossible. However, these discoveries often lead to transformative insights that shape the course of human knowledge and innovation. The journey to detect gravitational waves was marked by numerous setbacks and challenges, both technical and organizational. Early experiments by Joseph Weber in the 1960s failed to produce verifiable results, and skepticism about the feasibility of gravitational wave detection persisted for decades. LIGO itself faced crises related to noise interference, equipment failures, and funding pressures, any of which could have derailed the project. Despite these obstacles, the scientists and engineers involved demonstrated remarkable perseverance. They continuously refined their instruments, adapted to new challenges, and maintained their focus on the ultimate goal. The detection of GW 150,914 was the result of decades of incremental progress, where each small victory brought the team closer to success. This resilience offers an important lesson for both scientists and society at large. Meaningful progress often requires sustained effort over long periods. The ability to persist in the face of uncertainty and failure is a key factor in achieving breakthroughs, whether in science, technology, or other fields. Gravitational wave detection is a prime example of the power of collaboration in science. No single institution or nation could have achieved this success alone. The LIGO and Virgo collaborations brought together hundreds of researchers from diverse backgrounds, spanning multiple countries and disciplines. This global network of scientists, engineers, and administrators worked together to solve complex problems, share data, and improve the sensitivity of the detectors. The importance of collaboration extended beyond the scientific teams. Governments, funding agencies, and research institutions had to coordinate their efforts to support the project over several decades. The detection of gravitational waves demonstrated how large-scale scientific endeavors can foster international cooperation, even in times of political tension. The lesson here is that many of the greatest challenges facing humanity, such as climate change, space exploration, and global health, require a collaborative approach. Scientific discovery thrives when diverse perspectives and expertise are brought together to tackle complex problems. The pursuit of gravitational wave detection raises important questions about the ethics of scientific exploration and the allocation of resources. Critics have argued that projects like LIGO, which require significant financial and human resources, may not provide immediate practical benefits. In a world with pressing issues such as poverty, disease, and environmental degradation, some question whether investing in fundamental research is justified. However, history provides strong evidence that fundamental research often leads to unforeseen applications and societal benefits. Technologies developed for gravitational wave detection, such as precision optics and advanced data analysis methods, have already found applications in fields like medicine and communications. Moreover, the discovery itself has inspired millions by demonstrating the potential of human ingenuity and the importance of understanding our place in the universe. The ethical debate ultimately highlights the need for a balanced approach to resource allocation. While addressing urgent global challenges is critical, investing in science and discovery is equally important for the long-term advancement of society. The success of LIGO and Virgo underscores the profound relationship between scientific discovery and technological innovation. The detection of gravitational waves required unprecedented advancements in multiple fields, including precision engineering, quantum optics, and computational science. These innovations not only enabled the discovery, but also pushed the boundaries of what is technically possible. One of the key lessons from this achievement is that science and technology are deeply interconnected. Scientific questions often drive the development of new technologies, while technological advancements open new avenues for exploration. The iterative process of refining both theory and experimentation is essential for progress. This dynamic is evident in the ongoing efforts to develop next-generation gravitational wave detectors. Projects like the Einstein Telescope and Cosmic Explorer aim to build on the technological foundation established by LIGO and Virgo, with the potential to explore even deeper cosmic phenomena. These efforts exemplify the continuous cycle of discovery and innovation that characterizes modern science. The discovery of gravitational waves has had a profound cultural impact, inspiring people around the world to engage with science and wonder about the universe. The story of LIGO and Virgo, marked by vision, struggle, and triumph, resonates deeply with the human experience. It demonstrates that curiosity, creativity, and perseverance can lead to extraordinary achievements. Educational programs, documentaries, and popular science books have helped bring the story of gravitational wave detection to a global audience. This outreach has sparked renewed interest in STEM, science, technology, engineering, and mathematics, education, motivating young people to pursue careers in scientific research and innovation. The broader theme here is that science is not just a technical endeavor. It is a cultural and philosophical pursuit that enriches our understanding of existence. The success of gravitational wave detection serves as a powerful reminder of the importance of fostering a culture that values curiosity, exploration, and the pursuit of knowledge. As humanity looks to the future, the lessons from gravitational wave detection are both practical and philosophical. On a practical level, the achievement underscores the importance of investing in research infrastructure, fostering collaboration, and embracing innovation. These elements are crucial for addressing the complex challenges of the 21st century, from space exploration to climate science. On a deeper level, the discovery reminds us of the boundless potential of human curiosity and creativity. The quest to understand the universe is one of the most profound expressions of the human spirit. By continuing to explore and push the boundaries of knowledge, we reaffirm our place in the grand narrative of existence. Gravitational wave astronomy is still in its infancy, with many discoveries yet to come. Scientists are already planning new missions to detect waves from supermassive black holes, primordial cosmic events, and exotic phenomena beyond current theoretical models. These endeavors will build on the legacy of LIGO and Virgo, ensuring that the lessons of discovery and perseverance continue to inspire future generations. In summary, the broader themes and lessons of gravitational wave detection highlight the best aspects of human endeavor. They emphasize the importance of curiosity, collaboration, resilience, and the pursuit of knowledge, qualities that define the scientific enterprise and contribute to the advancement of civilization. The discovery of gravitational waves marks one of the greatest scientific milestones of the 21st century. It confirmed a key prediction of Einstein's general relativity and opened a new observational window on the universe. However, the story of gravitational wave detection is far from over. This final chapter summarizes the significance of the discovery, reflects on its impact across multiple domains, and looks ahead to the exciting future of gravitational wave astronomy and related scientific endeavors. The detection of GW 150,914 on September 14, 2015, was a defining moment in science. For the first time, researchers observed gravitational waves ripples in spacetime caused by the collision of two black holes. This achievement validated decades of theoretical and experimental work, overcoming skepticism and seemingly insurmountable technical challenges. It also demonstrated that humanity had developed the capacity to explore the universe in a fundamentally new way. Gravitational wave astronomy has since grown into a thriving field of research. By detecting additional events, such as binary neutron star mergers and multiple black hole collisions, scientists have gained new insights into cosmic phenomena that were previously hidden. These discoveries have confirmed long-standing theories, introduced new questions about the universe, and advanced our understanding of gravity, matter, and space-time. The significance of this breakthrough extends beyond physics. It has inspired advancements in engineering, computing, and quantum optics, with applications in fields such as medical imaging, communications, and precision measurement. Moreover, it has captured the imagination of millions, serving as a powerful example of what human collaboration and perseverance can achieve. Gravitational wave detection has had a transformative impact on science and technology, driving innovation across multiple domains, astrophysics and cosmology. The ability to observe gravitational waves has revolutionized our understanding of compact objects like black holes and neutron stars. It has also provided new ways to study the large-scale structure and evolution of the universe, including tests of cosmic expansion and dark matter theories. Precision measurement. The technologies developed for LIGO and Virgo, such as ultrastable lasers, seismic isolation systems, and quantum noise reduction, have set new standards for precision measurement. These innovations are being applied to other scientific experiments, including space missions and particle physics research, data science, and AI. The large volumes of data generated by gravitational wave detectors have driven advances in signal processing, machine learning, and distributed computing. These techniques are being adapted for use in industries ranging from finance to healthcare. Global collaboration. The success of LIGO and Virgo demonstrated the importance of international collaboration in tackling complex scientific challenges. This model of cooperation is being replicated in other large-scale research projects, such as efforts to combat climate change and explore deep space. While gravitational wave astronomy has made remarkable progress, it also faces significant challenges. One of the primary obstacles is the need for even greater detector sensitivity. To observe more distant and lower frequency events, such as supermassive black hole mergers, scientists must develop next-generation instruments with improved technology. Several major projects are already in development to address these challenges. Einstein Telescope, ET. Planned as a large underground observatory in Europe, the Einstein Telescope will feature triangular arms and enhanced noise isolation to detect both high and low-frequency gravitational waves. Cosmic Explorer. Proposed in the United States, this observatory will build on LIGO's success, with arms extending up to 40 kilometers to increase sensitivity. Cosmic Explorer is designed to detect events across vast cosmic distances, including those that occurred in the early universe. LISA, Laser Interferometer Space Antenna. A joint mission by NASA and the European Space Agency, ESA, LISA will be a space-based gravitational wave detector capable of observing low-frequency waves generated by supermassive black holes and other large-scale phenomena. These projects represent the future of gravitational wave astronomy, offering the potential to unlock new mysteries about the cosmos. Several new research avenues have emerged as a result of gravitational wave detection. Scientists are particularly excited about the following opportunities: primordial gravitational waves. Researchers hope to detect gravitational waves generated during the Big Bang, which could provide direct evidence for cosmic inflation and other early universe processes. Observing these waves would offer unprecedented insights into the origin of the universe. Black hole physics. Gravitational wave data has already challenged and refined existing theories about black holes. Future observations may shed light on unresolved questions, such as the nature of black hole singularities, event horizons, and quantum gravity. Exotic phenomena. Some scientists speculate that gravitational wave detectors could eventually observe phenomena beyond current models, such as dark matter interactions, cosmic strings, or topological defects in spacetime. These discoveries could revolutionize our understanding of fundamental physics. Multi-messenger astronomy. Success of events like GW 170,817 has demonstrated the power of combining gravitational wave data with electromagnetic and particle-based observations. Expanding this approach could lead to a more comprehensive view of cosmic events, from gamma-ray bursts to supernovae. The story of gravitational wave detection has become a source of inspiration for scientists, educators, and the public. It exemplifies the best aspects of human endeavor: curiosity, creativity, collaboration, and resilience. Educational programs and outreach efforts have introduced millions of people to the wonders of gravitational wave astronomy, fostering greater interest in science and technology. For young researchers entering the field, the success of LIGO and Virgo offers both motivation and opportunity. Many of the next-generation detectors will require new expertise in areas such as quantum computing, space-based engineering, and large-scale data management. These projects will provide a fertile ground for training the next wave of scientific leaders. The detection of gravitational waves is a testament to the power of long-term vision and collaboration. It represents the triumph of human ingenuity in overcoming seemingly impossible challenges. Through decades of hard work, scientists, engineers, and institutions demonstrated that even the most abstract ideas, such as ripples in spacetime, can become tangible and transformative discoveries. Looking to the future, gravitational wave astronomy is poised to continue expanding our understanding of the universe. As new detectors come online and technologies improve, humanity will gain access to deeper and more detailed insights into the cosmos. This ongoing journey of discovery reaffirms a central truth about science. The pursuit of knowledge is not only a practical endeavor, but also a deeply philosophical one, driven by the need to understand our place in the grand tapestry of existence. In this spirit, the legacy of gravitational wave detection will endure as a symbol of exploration and discovery. An enduring reminder that the universe still holds countless secrets waiting to be revealed.